Welcome to Still Science Lab. Tonight, we explore one of the most ambitious questions ever asked in modern physics. What if every particle, every force, every structure in the universe came from one deeper pattern? What if the complexity of matter, gravity, light, space-time, and quantum behavior was not a collection of separate rules, but different expressions of a single underlying language? This is the dream behind string theory, not a small idea, not a minor correction, but a framework that tried to reach beneath the known particles of nature, beneath the familiar forces, beneath the geometry of space-time itself, and ask whether everything could be understood as variations of one deeper structure. For decades, string theory has occupied a strange place in physics. It is one of the most mathematically rich and influential ideas ever developed. It has reshaped the way theorists think about quantum gravity, black holes, extra dimensions, holography, and the relationship between geometry and information. It has produced tools that reached far beyond its original goals. It has inspired generations of physicists to imagine a universe more unified than the one our current theories seem to show. And yet, it has not been experimentally confirmed as the final theory of nature. That tension is what makes it so fascinating. String theory is powerful because it tried to turn the universe's complexity into one underlying language. But science does not accept beauty alone. A theory must answer to nature. It must face evidence. It must explain the universe we observe, not merely the universe that mathematics allows. So string theory lives between two worlds. On one side, a dream of unity. On the other, the hard silence of experiment. To understand why anyone would attempt something as bold as string theory, we have to begin with the state of physics itself. Modern physics is extraordinarily successful, but it is not complete. It rests on two great pillars that have changed our understanding of reality more deeply than almost anything before them. One pillar is quantum mechanics, the theory of the small. It describes atoms, particles, fields, radiation, and the strange rules that govern the microscopic world. It tells us that matter is not simply made of tiny classical objects, that probabilities are built into prediction, that measurement matters, and that particles can behave in ways ordinary intuition was never designed to understand. The other pillar is general relativity, the theory of gravity and space-time. It tells us that gravity is not simply a force pulling objects through space, but a manifestation of curved space-time. Massive objects shape the geometry around them. Planets move along paths through that geometry. Black holes form when space-time curves so strongly that not even light can escape. The universe itself can expand. Both theories work with extraordinary precision. Together, they explain much of what we see, but together, they do not fit easily. Quantum mechanics speaks in the language of probabilities, fields, uncertainty, and discrete interactions. General relativity speaks in the language of smooth geometry, curvature, and space-time. One governs the microscopic, the other governs the cosmic. For most practical purposes, they can be used separately. Atoms do not require the full machinery of curved space-time. Planetary orbits do not usually require quantum uncertainty, but there are places where separation fails. Inside black holes, at the beginning of the universe, at scales where gravity becomes quantum, at moments where space-time itself may no longer behave like a smooth background. There, the two pillars must somehow meet. And when they meet, the equations begin to strain. This is the deep problem string theory tried to address. Physics needed a theory of quantum gravity, a framework where gravity could be understood in a way consistent with quantum mechanics, not as an afterthought, not as a patch, but as part of a deeper structure that could include particles, forces, and space-time itself. The idea that emerged was radical. Maybe the fundamental ingredients of nature are not point-like particles. Maybe they are tiny strings. Not strings in the everyday sense. Not little threads made of material. Not tiny wires floating in space. But one-dimensional quantum objects whose different vibrational patterns could appear to us as different particles. In this picture, an electron, a quark, a photon, and other particles are not fundamentally different kinds of point-like things. They may be different modes of vibration of the same underlying type of object. Like different notes from a single instrument, different vibrations could produce different physical properties: mass, charge, spin, and interaction. The metaphor is useful, but it must be handled carefully. String theory is not confirmed by direct observation. No one has seen a fundamental string. These strings, if they exist, would be far smaller than anything current experiments can probe directly. They are not physical strings in the ordinary sense. They are mathematical objects in a theoretical framework. But the idea offered something remarkable. When physicists tried to build quantum theories of point-like particles, gravity resisted. The mathematics became difficult in ways that seemed to produce infinities and breakdowns. But when the basic object was extended, when a particle was replaced by a tiny string, some of those problems softened. The string's finite size changed the behavior of interactions at extremely small scales. Even more striking, string theory seemed to naturally include a particle with the properties expected of the graviton, the hypothetical quantum carrier of gravity. That was one of the reasons the theory became so compelling. It was not originally invented simply to solve quantum gravity, but it began to look like a framework where gravity was not forced in from the outside. It appeared as part of the structure. For physicists searching for unity, this was hard to ignore. A theory that could contain quantum mechanics and gravity. A theory that could connect particles and forces. A theory that suggested the universe's diversity might arise from one deeper kind of object. It sounded like the beginning of a theory of everything, but the dream became more complicated. String theory did not simply describe the familiar 3 dimensions of space and 1 dimension of time. To be mathematically consistent, it required extra dimensions. Dimensions beyond the ones we experience directly. These dimensions might be compactified, curled up into shapes so small that we do not notice them in everyday life. Their geometry could influence the properties of particles and forces, meaning that the hidden shape of space might help determine the visible laws of physics. This was breathtaking. It was also troubling, because the same flexibility that made string theory rich also made it difficult to test. There were many possible ways the extra dimensions could be shaped, many possible solutions, many possible universes in the mathematics. Instead of one clear prediction, the theory seemed to open a vast landscape of possibilities. A dream of one theory began to look like a maze. This is where the story becomes scientifically delicate. String theory has not failed in a simple way. It has not been disproven by one decisive experiment, but it has also not delivered the kind of clear, unique experimental prediction that would confirm it as the final description of nature. Its characteristic scales may be far beyond what particle accelerators can reach. Its possible solutions may be too numerous to point cleanly to our universe. Its mathematical beauty has not yet become direct experimental evidence. That is the heart of the controversy. String theory tried to explain everything, but nature has not yet said yes, and still, it changed physics. That is one of the most interesting parts of the story. Even without final confirmation, String theory produced ideas that transformed other fields. It helped deepen the study of black holes. It contributed to the holographic principle, the idea that information in a volume of space might be described by degrees of freedom on a boundary. It connected gravity to quantum theories in surprising ways. It created mathematical tools used in areas far beyond its original purpose. It forced physicists to think differently about space-time. Maybe space-time is not fundamental. Maybe geometry emerges from deeper quantum relationships. Maybe gravity and information are more closely connected than anyone expected. Maybe black holes are not just cosmic traps, but clues to the deepest architecture of reality. These are not small contributions. They are part of why string theory remains important even to those who question whether it is the final theory. It became more than a proposed explanation of particles. It became a generator of ideas, a framework that opened doors in theoretical physics and mathematics. But the central question remains, is string theory describing our universe, or is it showing us a path towards something still deeper? That question cannot be answered by elegance alone. Physics is not poetry, even when its ideas are beautiful. A theory must make contact with observation. It must explain measurable reality. It must survive the pressure of evidence. The universe is not required to follow the most elegant equation we can write. This is the humility at the core of the story. String theory is one of the most beautiful ideas in physics, but beauty is not proof. At the same time, lack of proof is not the same as uselessness. Some theories take time before their experimental consequences become accessible. Some frameworks become valuable by revealing connections, even before they are confirmed as final truth. Some ideas reshape the questions we ask, and in doing so, change the direction of science. String theory belongs to that difficult category. It is not confirmed reality. It is not empty fantasy. It is an ambitious mathematical framework that tried to unify the deepest laws we know, and in trying, it transformed the landscape of theoretical physics. There is something profoundly human in that attempt. The universe appears fragmented from our position, matter here, light there, gravity on cosmic scales, quantum behavior in laboratories, black holes in distant space, particles in accelerators, space-time in equations. We study pieces because pieces are what we can measure. But the mind searches for unity. It asks whether the pieces belong to a whole. String theory was one of the boldest attempts to answer yes. It imagined that the universe's many particles might be different vibrations of the same underlying structure. It imagined that forces and matter could arise from one framework. It imagined hidden dimensions shaping the laws we observe. It imagined that gravity could be quantum, that space-time could be part of a deeper order, and that the complexity of reality might be written in a language more unified than anything we had before. Whether that language is the final language remains unknown, and that uncertainty is not a weakness to hide. It is part of honest science. The dream of one theory is still alive, but it is not complete. String theory stands as both a monument to human imagination and a reminder that imagination must answer to the universe. It shows what physics can become when mathematics reaches toward the deepest possible unity. It also shows how difficult it is to prove that such unity is not only beautiful, but real. The universe may still be waiting, not silent forever, but not yet convinced. And so string theory remains suspended between promise and proof, between roots and fruits, between the desire to explain everything and the discipline of admitting what has not yet been shown. Its power lies in that tension, a theory that tried to turn particles, forces, gravity, and space-time into one underlying language. a beautiful idea still searching for the voice of nature to answer back. Physics did not reach for string theory because the universe looked simple. It reached for something deeper because the universe looked divided. By the end of the 20th century, modern physics had built two extraordinary descriptions of nature. Each one changed reality at its foundations. Each one passed experimental tests with astonishing success. Each one revealed that common sense was only a local habit, useful at human scale but not final. One of these descriptions was quantum mechanics. The other was general relativity. Quantum mechanics became the language of the microscopic world. It described atoms, particles, radiation, fields, probability, uncertainty, and the strange behavior of matter at the smallest scales we can probe. It explained why atoms are stable, how electrons occupy quantum states, why light comes in quanta, how chemical bonds form, and how the technologies of the modern world can exist. Semiconductors, lasers, magnetic resonance imaging, atomic clocks, and much of modern electronics all depend on quantum rules. It is not a vague theory. It is one of the most accurate frameworks ever created. But it is deeply strange. At the quantum level, particles do not behave like tiny classical objects. They can be described by states that contain possible outcomes. They can interfere like waves. They can be entangled so that the full information of a system belongs to relationships, not separate pieces. Measurement does not simply reveal the world in the ordinary way. It plays a role in producing definite records from quantum possibilities. Quantum mechanics taught physics that nature, at its foundation, does not always follow the logic of everyday objects. General relativity changed the universe from the other direction. It became the language of gravity, space-time, and the cosmos. Before relativity, gravity could be imagined as a force pulling objects across space. General relativity replaced that picture with something deeper. Gravity became the geometry of space-time itself. Matter and energy shape space-time. Curved space-time guides the motion of matter and light. This idea explained the orbit of planets more precisely. It predicted the bending of light by gravity. It predicted gravitational time dilation. It predicted black holes. It made possible the modern understanding of an expanding universe. It turned space and time from a passive stage into a physical structure with its own behavior. General relativity taught physics that the universe is not merely filled with objects. The geometry in which objects exist is also part of reality. So modern physics had two pillars, one for the small, one for the large, one for particles, atoms, and quantum fields, one for gravity, space-time, and the cosmic scale. Each pillar was powerful, each was tested, each was necessary, but they did not fit together easily. For most situations, this was not a practical disaster. If you are calculating the behavior of an electron in an atom, gravity is so weak that it can usually be ignored. Quantum mechanics does the work. If you are calculating the orbit of a planet, quantum uncertainty is irrelevant. General relativity, or even ordinary gravity, in many cases, does the work. The two theories can live separately because most of the universe allows them to operate in different domains. But physics does not only ask about ordinary domains. It asks about the places where the separation breaks, and those places are some of the most extreme and important in the universe. Black holes are one of them. A black hole is a region where gravity becomes so intense that space-time curves into a one-way boundary. Beyond the event horizon, escape becomes impossible for anything moving forward in time, even light. General relativity describes black holes with remarkable elegance. It tells us how they form, how they curve space-time, how objects fall toward them, and how their horizons behave. But black holes also raise quantum questions. If matter falling into a black hole carries information, what happens to that information? Is it lost? Is it hidden? Is it returned in some subtle form through radiation? Quantum mechanics suggests that information should not simply disappear from the universe. General relativity, taken too directly, seems to allow a black hole to hide information behind a horizon and perhaps erase it at a singularity. This is not a small technical issue. It is a clash between deep principles. Black holes force quantum theory and gravity into the same room. Near the singularity, the problem becomes even more severe. General relativity predicts that matter can be compressed to a point of infinite density, where curvature becomes infinite and the equations break down. Infinities in physics often signal that a theory has reached the edge of its domain. They do not necessarily mean nature literally contains an infinite physical quantity. They may mean that the theory is being pushed beyond where it can be trusted. At the heart of a black hole, gravity is extreme. Quantum effects should matter, but we do not yet have a complete theory that describes space-time itself quantum mechanically. The Big Bang presents a similar problem. General relativity tells us that the universe has expanded from an earlier, hot, dense state. Run the equations backward far enough, and density and curvature increase toward a beginning where the classical theory can no longer be trusted. The early universe was small, dense, hot, and energetic in a way that demands both quantum physics and gravity. Quantum fields were active. Space-time was dynamic. Energy scales were extreme. The smooth geometry of general relativity and the probabilistic structure of quantum mechanics had to be part of the same reality. But our best theories do not fully merge there. This is one of the deepest reasons physics needed something beyond the existing framework, not because quantum mechanics failed in the laboratory, not because general relativity failed in the solar system or around black holes at observable scales. They succeeded brilliantly. The problem was that their successes pointed towards situations where both had to be true at once. A complete picture of nature cannot simply say, use one theory here, another there, and never ask what happens at the boundary. The universe does not divide itself according to our convenience. At extreme energy scales, the problem becomes unavoidable. In particle physics, high energy allows smaller distances to be probed. To understand what happens at the deepest possible scales, gravity may no longer be negligible. But when physicists tried to treat gravity like the other quantum forces, using the familiar methods of quantum field theory, the mathematics became difficult in a fundamental way. Calculations produced uncontrollable infinities. The theory did not behave like the quantum theories of electromagnetism, the weak force or the strong force. Gravity resisted quantization. This did not mean quantum gravity was impossible. It meant the old methods were not enough. The known forces of the standard model fit into quantum field theory. They are described through fields and particles, symmetries, and interactions. This framework has been extraordinarily successful for the microscopic world. But gravity, in general relativity, is not simply another force acting within space-time. It is the behavior of space-time itself. To quantize gravity, we may need to quantize the stage, not just the actors. That is much harder. If space-time is dynamic, then a quantum theory of gravity cannot merely place quantum particles inside a fixed background. It has to explain what space-time is at the deepest level. It has to explain whether space and time remain smooth, whether they become discrete, whether they fluctuate, whether they emerge from something more basic. It has to explain what happens when geometry itself becomes subject to quantum rules. This is the root problem. The smallest rules of matter and the largest rules of space-time are both successful, but incomplete together. String theory grew from this tension. Its earliest roots did not begin exactly as a theory of everything. It first emerged in attempts to understand the strong nuclear force, before quantum chromodynamics became the accepted theory of quarks and gluons. But the mathematical structure of string theory revealed something unexpected. When physicists studied tiny one-dimensional objects rather than point-like particles, the theory naturally included a kind of excitation that looked like a quantum particle of gravity. This was remarkable. The theory seemed to contain gravity without having to force it in afterward. That shifted the meaning of the idea. What began in one context became a candidate for a deeper framework. If particles were not fundamental points, but tiny vibrating strings, then perhaps the infinities that plagued quantum gravity could be softened. A point-like interaction happens at an exact location with no size. A string has extension, however tiny. Its interactions are spread out over a small region. That difference can change the behavior of the mathematics at extreme scales. The idea was bold. Maybe the failure came from imagining the fundamental ingredients as points. Maybe nature's deepest building blocks are extended objects. Maybe particles are different vibrational patterns of strings. Maybe gravity, matter, and forces can arise from the same underlying framework. This was not an arbitrary fantasy. It was motivated by a real problem, the need to reconcile quantum mechanics with general relativity. String theory offered one of the most developed attempts to do that. It suggested that the distinction between particles and forces might be less fundamental than it appears. It suggested that space-time itself might be part of a richer structure involving extra dimensions and deeper mathematical relationships. The roots of string theory therefore lie in both crisis and ambition. The crisis was that the two great pillars of physics did not unify smoothly. The ambition was that perhaps the conflict could be resolved by changing the basic picture of what the universe is made of. Instead of point particles moving through space-time, perhaps the deepest objects are strings whose vibrations create the particles we observe. Instead of gravity being an incompatible force added to quantum theory, perhaps gravity emerges naturally from the same string framework. Instead of space-time being a fixed background, perhaps its geometry is tied to the deeper rules of the theory. The appeal was not only mathematical elegance, it was the possibility of unity. Physics has seen unity before. Electricity and magnetism were once separate phenomena, then became electromagnetism. The weak force and electromagnetism were later connected in the electroweak theory. The Standard Model organized particles and three forces into one powerful framework, though it left out gravity, general relativity, unified gravity with the geometry of spacetime. Again and again, progress came when apparently separate things turned out to be different faces of one deeper structure. String theory extended that hope further than almost any idea before it. It asked whether all particles, all forces, and gravity itself might be part of one coherent framework. But the very scale of the ambition created its own challenge. A theory of quantum gravity must reach domains far beyond ordinary experiment. The energies where quantum gravitational effects become directly obvious may be unimaginably high compared with what our current accelerators can achieve. Black holes and the early universe offer clues, but not easy laboratory access. Nature protects its deepest regimes behind distance, energy, and scale. This is why string theory grew in a difficult environment. It was motivated by real physical problems, but often developed through mathematics rather than direct experimental guidance. It sought to describe regions where our current instruments cannot easily go, That gave it freedom, but also danger. Freedom to explore deep structures, danger of drifting too far from testable evidence. Still, the motivation remains powerful. Quantum mechanics and general relativity cannot both be the final word in their current separate forms. Somewhere, in the deep structure of nature, they must be reconciled. Black holes demand it. The early universe demands it. The logic of physics demands it. If matter is quantum and gravity is spacetime, then the universe needs a way for quantum matter and spacetime geometry to belong to one consistent story. String theory was one of the boldest attempts to write that story. Its roots are not simply in elegance or imagination. They are in the unfinished foundation of modern physics. At the smallest scales, quantum mechanics tells us the world is made of states, fields, uncertainty, and discrete interactions. At the largest scales, general relativity tells us the world is made of curved spacetime, gravity, horizons, and cosmic expansion. The places where these truths meet are the places where our understanding becomes incomplete. String theory grew from the need to reconcile the smallest rules of matter with the largest rules of spacetime. It was born from the realization that physics had two languages for one universe, and somewhere beneath both, there might be a deeper language still waiting to be understood. At the deepest level we have tested, nature is described in terms of particles and fields, electrons, quarks, photons, gluons, neutrinos, the Higgs boson. Each one has its own properties, its own role, its own way of interacting with the rest of the universe. Some build atoms, some carry forces, some pass through matter almost untouched. Some exist only briefly before transforming into something else. The Standard Model organizes these particles with extraordinary precision. It tells us how matter behaves, how forces act, and why the microscopic world has the structure we observe. It is one of the greatest achievements in the history of science. But in the usual formulation of particle physics, fundamental particles are treated as point-like. They have no size in the ordinary sense, no surface, no edge, no tiny internal shape that experiments have revealed. They are represented as localized excitations of fields, and when we calculate their interactions, they often behave as if their fundamental structure has no spatial extent at all. That point-like picture works extremely well for known particle physics. But when gravity enters the story, point-like objects create trouble. At extremely small scales and high energies, the mathematics of quantum gravity becomes unstable when interactions are forced into exact points. The infinities that appear are not just inconvenient. They suggest that the theory is being pushed beyond its proper form. Nature may not actually allow the deepest interactions to be compressed into a perfect mathematical point. String theory begins with a different possibility. What if the most fundamental ingredients are not points? What if they have a tiny extension? What if, beneath the particles we observe, there are one-dimensional objects, strings, vibrating in different ways? This is the basic idea. Not tiny strings in the everyday sense, not little threads made of matter, not microscopic wires stretched through space. A string in string theory is a mathematical object, an extremely small extended structure whose possible vibrations could correspond to what we perceive as particles. The shift sounds simple. Point becomes string, but that small change transforms the entire picture. A point particle has no internal length. A string has extension, even if unimaginably tiny. A point particle moves through spacetime like a point tracing a path. A string sweeps out a surface as it evolves. A point particle is one kind of mathematical idealization. A string is another, richer one. And because a string can vibrate, it can have different modes. Those different vibrational patterns are the heart of the idea. In ordinary life, one instrument can produce many notes. A violin string, a guitar string, or a piano string can vibrate in different patterns, producing different sounds. The string is the same underlying object, but the vibration changes what we hear. One pattern becomes one note, another pattern becomes another note. String theory borrows that intuition, but on a far deeper level. In this framework, different particles may not be fundamentally separate kinds of things. They may be different vibrational states of the same underlying string. One mode of vibration could appear as an electron, another could appear as a quark, another could appear as a photon, another could appear as a particle associated with gravity. Different particles would then be like different notes played by one deeper instrument. This is only an analogy, and it should not be taken too literally. A fundamental string is not vibrating through air. It is not making sound. It is not a material string plucked inside space like a musical instrument. The vibration is a quantum and mathematical pattern, not a mechanical motion in the familiar sense. But the analogy captures the central emotional idea: diversity from unity, many particles from one structure, a universe of apparent complexity from a deeper pattern of allowed vibrations. This is why string theory became so compelling to many physicists. It offered a way to imagine that the long list of particles in nature might not be a list of separate fundamentals. Perhaps they are related. Perhaps their properties arise from deeper conditions. Perhaps mass, charge, spin, and interaction are not arbitrary labels attached to independent particles, but consequences of how a more basic object can vibrate. The particle becomes a note. The string becomes the underlying source. In this picture, what we call particles are not the final alphabet of nature. They are the sounds made by something deeper. The standard model names the notes. String theory asks about the instrument. The promise is enormous. If particles are different expressions of one vibrating structure, then the universe may be more unified than it appears. Matter particles and force particles might share a common origin. Gravity might enter the same framework as the other interactions. The distinction between particle types might be less fundamental than the rules governing strings. This does not mean string theory has been proven. It has not. No experiment has directly observed a fundamental string. No particle accelerator has reached the scale where such strings would reveal themselves directly if they exist in the simplest versions of the theory. The strings are expected to be so small that they lie far beyond current experimental reach. For now, they are part of a mathematical framework, not directly detected physical objects. That point is essential. String theory is not confirmed reality. It is a proposed framework, a powerful, elegant, controversial framework. Its value comes from what it attempts to solve, the connections it reveals, and the mathematical structures it produces. But it remains unverified as the final description of the universe. The difference between a confirmed particle and a theoretical string is important. Electrons are observed through their effects again and again. Photons are measured in countless experiments. Quarks are inferred through high-energy scattering and the behavior of particles made from them. The standard model has direct experimental support across enormous ranges of data. Fundamental strings, by contrast, have not been observed. They are not objects we have found. They are objects the theory proposes. The question is whether nature actually uses them, and that question remains open. Still, the idea of replacing point particles with strings has deep consequences. One of the most important is that string theory naturally changes how interactions behave at extremely small scales. If a particle is treated as an exact point, interactions can become sharply concentrated, leading to mathematical problems when gravity is included. A string spreads interaction over a tiny extended region. That extension can soften the behavior of the theory. This was one of the reasons string theory looked promising as a theory of quantum gravity. It did not simply add gravity as another force by hand. In many versions of the theory, a vibrational mode appears, with the properties expected of the graviton, the hypothetical quantum particle associated with gravity. That was a stunning clue. A framework built from strings seemed to contain gravity as a natural part of its structure. For physicists searching for a unified theory, that mattered deeply. It suggested that gravity might not be an outsider. It might be one of the notes, one vibrational pattern among others. If so, then the force that shapes planets, stars, black holes, and the expansion of the universe could share a foundation with the particles that build atoms. The smallest and the largest would no longer be governed by separate languages. They would be connected through a deeper mathematical structure. This is the dream at the center of string theory, but the dream comes with difficulty. Strings are not easy to visualize, and the full theory is not simple. It often requires extra dimensions beyond the ones we experience. It involves complex mathematical spaces, symmetries, dualities, and possible configurations. It does not produce a single obvious universe without additional choices. The same richness that gives it power also makes it hard to test. The simple image of tiny vibrating strings is only the entrance. Behind it lies an enormous theoretical landscape. That is why responsible storytelling about string theory must balance wonder with caution. The idea is beautiful, but beauty is not proof. The analogy is powerful, but analogy is not evidence. The mathematics is rich, but the universe must decide whether the mathematics describes reality. Still, even as an unconfirmed framework, the move from particles to strings changed how physicists thought. It questioned whether point-like particles are truly fundamental. It offered a new way to include gravity in quantum theory. It suggested that particle properties might arise from deeper vibrational states. It connected the physics of matter with the geometry of hidden dimensions. It opened paths into black holes, holography, and the possible emergence of spacetime. The idea was not simply that particles are tiny strings. The deeper idea was that particles may not be the deepest layer. They may be appearances, low-energy expressions, observable consequences of a structure too small and too subtle to see directly. In everyday science communication, it is easy to imagine string theory as a replacement picture. Instead of little dots, think little strings. But that is only the first step. The more profound shift is that the identity of a particle becomes relational. It depends on the state of the string, the way it vibrates, the geometry it occupies, and the conditions of the larger theory. A particle is no longer a separate fundamental object. It is a pattern. That word matters. Physics has often moved from objects to patterns. Heat became molecular motion. Light became electromagnetic radiation, then quantum field excitation. Matter became atoms, then particles, then fields. Gravity became space-time geometry. Again and again, what first looked like a thing became behavior in something deeper. String theory continues that motion. Particles become vibrational patterns. Forces become connected to those patterns. Space-time becomes part of the larger framework. The universe becomes less like a collection of separate building blocks and more like a system whose visible pieces arise from hidden structure. This is why the musical analogy remains so persistent. It is imperfect, but it captures something important. The same underlying entity can produce many different expressions. The universe may not need a separate fundamental object for every particle. It may need a deeper rulebook that determines which vibrations are possible. In that sense, string theory tries to explain why the particle zoo exists at all. Why these particles? Why these properties? Why these forces? Why gravity? Why quantum mechanics and spacetime together? It does not yet answer these questions in a confirmed way, but it gives them a unified form. It turns the list of particles into a question about deeper structure, and that is a major intellectual shift. The Standard Model is like an incredibly accurate catalogue of the known particles and their interactions, except for gravity. String theory asks whether the catalogue itself comes from a deeper source. It does not deny the catalogue. It tries to explain why the catalogue might exist. But here, humility must remain. If fundamental strings exist, they are far beyond direct observation with present technology. We cannot simply magnify matter and see them vibrating. We cannot point to a detector track and say, there is a string. The evidence, if it ever comes, may be indirect, through predictions about particles, cosmology, gravity, black holes, or mathematical consistency that connects to observation in a way we have not yet achieved. Until then, string theory remains a profound possibility, not established fact. This status can feel frustrating, but it is part of the honest frontier of physics. The deepest questions often begin before the evidence is fully accessible. Theories are developed, tested where possible, criticized, refined, and sometimes abandoned. Some become confirmed, some become tools, some become bridges to better theories. Some change the questions, even if they do not become final answers. String theory may be any of these, but the central idea remains one of the most striking in modern thought. Perhaps particles are not the ultimate ingredients. Perhaps they are different expressions of one deeper vibrating structure. Perhaps the universe's complexity is not a collection of disconnected facts, but the result of hidden patterns at scales far beyond ordinary reach. A photon, an electron, a quark, and a graviton would then not be separate mysteries, but different ways a deeper object can exist. Different notes in a theory that tries to make nature's music into mathematics. Not music in the literal sense. Not strings we can hear, but patterns, allowed states, vibrations in the deepest language physics has imagined. That is the move from particles to strings, a move from points to extended objects, from many fundamentals to one possible source, from a catalogue of particles to a hidden grammar of vibration. And whether or not nature ultimately chooses string theory, the idea remains one of the boldest attempts to ask what matter, force, and space-time might be beneath the surface of the known world. String theory asks us to imagine that reality may have more directions than we can move through. That idea sounds almost impossible at first, because human experience is built inside 3 dimensions of space. We can move left and right, forward and backward, up and down, add time, and we have the familiar arena of experience, events happening somewhere, at some moment, inside space-time. Every object we touch, every path we walk, every star we locate in the sky seems to belong to this structure. 3 dimensions of space, 1 dimension of time. That is the world our bodies know. But string theory often requires more, not as an optional decoration, not as a casual speculation added to make the universe more mysterious. In many versions of the theory, extra dimensions are required for the mathematics to work consistently. If the fundamental ingredients of nature are tiny vibrating strings, then the space in which those strings vibrate cannot always be limited to the dimensions we directly perceive. The theory points toward hidden directions of space dimensions beyond the familiar three, woven into the structure of reality in ways too small or too subtle for ordinary senses to detect. This is one of the most famous and difficult ideas in string theory. The universe may contain more dimensions than experience reveals. At first, that sounds like fantasy, but in physics, a dimension is not a magical realm. It is a direction in which something can vary or move. A line has one dimension, a surface has two, ordinary space has three. Time adds another kind of dimension, one tied to change, sequence, and causality. To speak of extra dimensions is to ask whether there are additional degrees of spatial freedom hidden from our direct awareness. The challenge is obvious. If extra dimensions exist, why do we not see them? Why can we move through only three spatial directions? Why does everyday life not reveal the hidden geometry? One answer, offered by string theory, is compactification. The extra dimensions may be curled up, compact, and incredibly small. They may exist at scales so tiny that ordinary particles, atoms, bodies, and instruments do not move through them in any obvious way. The familiar three dimensions may be large and extended, while the extra dimensions are folded into intricate shapes at every point in space. This is difficult to picture, but the basic idea can be approached carefully. Imagine something that appears one-dimensional from far away, like a thin cable stretching into the distance. From a great distance, only the length is obvious, but up close, the cable has a circular direction around it. A tiny creature small enough to move on its surface could travel along the length or around the circumference. What appeared to have one dimension from far away actually has another direction hidden by scale. This analogy is imperfect, but it helps. A dimension can be real and still be hidden if it is curled up too small to notice. String theory applies this idea at scales far beyond ordinary imagination. The extra dimensions would not be large hidden rooms beside our universe. They would not be parallel spaces we could enter with a doorway. They would be part of the geometry of space itself, curled into shapes so tiny that they affect the deepest behavior of particles and forces without appearing as visible directions. The hidden dimension is not far away. It may be everywhere, curled into the structure beneath ordinary space. This is where the idea becomes powerful. In string theory, the shape of the extra dimensions is not just background scenery. It can influence what particles exist, how they behave, and what forces appear in the larger universe. The way a string vibrates depends on the space available for vibration. If the hidden dimensions have one shape, certain vibrational patterns may be allowed. If they have another shape, the particle spectrum and interactions may change. In other words, particle physics may depend on geometry, not just the geometry of the large-scale universe, but the hidden geometry of dimensions too small to see. This is a profound shift. In ordinary physics, we often think of particles as having fixed properties: mass, charge, spin, and interaction strengths. The Standard Model lists these particles and describes how they behave with remarkable success, but it does not fully explain why the particle properties are exactly what they are. It tells us the rules, but many numbers and structures still appear as inputs. String theory suggests a deeper possibility. Maybe some of those properties are not arbitrary. Maybe they arise from the shape of hidden dimensions. The geometry beneath space could help determine the physics above it. A string vibrating in a simple hidden space might produce one set of particles. The same string vibrating in a more complex hidden geometry might produce another. The hidden shape becomes like an instrument, and the particles are the notes that instrument can produce. Change the shape, and the music changes. Again, the analogy is only an entry point. The mathematics of compact dimensions is much more precise and much more difficult than a musical image. But the central idea remains. What we call the laws of particle physics may be linked to the structure of dimensions we cannot directly observe. This gives string theory both beauty and trouble. The beauty is that it connects things that once seemed separate: geometry and particle physics, space and matter, shape and force. Instead of treating the properties of particles as disconnected facts, string theory asks whether they emerge from a deeper geometric order. The universe's complexity might be partly written into hidden dimensions. The trouble is that there may be many possible shapes, very many. The extra dimensions can be curled up in different ways. Each way may lead to different low-energy physics, different particles, different forces, different constants, different possible universes. This is part of what is often called the landscape of string theory, a vast collection of possible solutions, each corresponding to a different hidden geometry or vacuum state. This makes testing difficult. If the theory allowed only one possible shape, and that shape predicted exactly the particles and forces we observe, the situation would be cleaner. But if there are many possible compactifications, then string theory may not immediately give one unique prediction for our universe. It may describe a broad space of possible universes, and our observed physics would correspond to one particular region of that space. That raises deep questions. Why this shape? Why these dimensions? Why these forces? Why these particles? Why this universe? Some physicists see the landscape as a problem because it weakens the theory's predictive power. Others see it as a clue, perhaps connected to cosmology, the multiverse, or selection effects. The debate remains unresolved. What matters here is that extra dimensions do not simply make string theory exotic. They make it rich, flexible, and hard to pin down experimentally. A beautiful idea becomes a complex maze. Still, the core concept remains one of the most striking in modern physics. Hidden geometry may shape visible reality. We already know that geometry can have physical consequences. General relativity taught us that the curvature of spacetime is gravity. The path of planets, the bending of light, the slowing of time near massive objects, all of these are consequences of geometry. Space and time are not passive. Their shape affects what matter does. String theory extends that intuition into the unseen. Maybe the shape of dimensions too small to observe affects the kinds of particles and forces that can exist. Maybe the laws we measure are shadows of hidden geometry. This is not confirmed. It is not established experimental fact, but it is a powerful theoretical possibility, and it changed the way physicists think about the relationship between matter and space. In this view, the electron's properties might not be just isolated facts. The forces might not be unrelated rules. The number of particle families, the patterns of interaction, and the presence of certain symmetries could be connected to the structure of the extra dimensions. The hidden space would not merely contain physics. It would help create the form physics takes. That is a startling thought. The universe we experience may be the visible surface of a deeper geometric structure. There is also a subtle philosophical shift here. We tend to assume that reality is limited to what can be directly pictured. If we cannot move through a direction, we are tempted to say that direction does not exist. but physics has often expanded reality beyond ordinary movement. We do not see curved spacetime directly, but we measure its effects. We do not see quantum fields with our eyes, but their excitations build matter and light. We do not see the interior of a black hole, but our theories reveal the boundary of what can be known from outside. Extra dimensions, if they exist, would belong to this tradition, not obvious, not intuitive, possibly real through their consequences. Science cannot accept them merely because they are mathematically elegant, but it also cannot reject them simply because human bodies cannot sense them. Our senses evolved for survival on a planet, not for detecting the full architecture of spacetime. If extra dimensions are curled up at scales beyond ordinary reach, the fact that we do not feel them is not surprising. The question is not whether they are easy to imagine. The question is whether nature requires them. For now, that question remains open. No experiment has directly confirmed the extra dimensions of string theory. Particle accelerators have not revealed clear signs of them. Gravity experiments have not shown unmistakable deviations that prove hidden spatial directions. Cosmology has not yet delivered a signal that confirms a particular compactification. The idea remains part of a theoretical framework, still waiting for decisive contact with observation. But even unconfirmed, it has influenced physics deeply. It encouraged physicists to think of geometry as more than the large-scale shape of spacetime. It connected the possible laws of nature to the topology and structure of hidden spaces. It enriched mathematics. It inspired new ways to think about dualities, where two very different-looking descriptions can represent the same underlying physics. It helped push the idea that spacetime itself might not be the final layer. Extra dimensions are therefore not just a strange add-on, they are part of the way string theory tries to make unity possible. If strings are the fundamental objects, they need a space of sufficient structure to vibrate consistently. If their vibrations become particles, then the geometry of the space they inhabit can shape the particle world. If gravity emerges naturally in the framework, then spacetime and hidden dimensions become central to the theory's meaning. The invisible geometry becomes part of the explanation. This is why string theory feels so different from ordinary particle physics. It does not simply add another particle to the list. It changes the background assumptions. It says that the catalogue of particles may depend on dimensions we cannot see. It suggests that what appears as particle physics in our large four-dimensional experience may be the result of a higher dimensional structure folded into every point of space. The familiar universe becomes a lower dimensional face of something deeper. That idea is difficult to hold without exaggeration. It should not be turned into fantasy worlds or simple parallel universes. The extra dimensions of string theory are not necessarily places where alternate versions of ourselves live. They are not science fiction realms beside our own. They are proposed hidden directions in the mathematical structure of space-time, likely compactified at scales far too small for direct access. Their importance is not that we could travel through them. Their importance is that they may shape the laws we observe. This returns us to the central idea. String theory suggests that what we call particle physics may depend on hidden geometry beneath ordinary space. The particles we measure, the forces we study, and the constants we place into equations may not be final, unexplained facts. They may be consequences of a deeper shape, a shape hidden from the body, hidden from the eye, hidden even from current instruments, but perhaps written into the structure of reality itself. If true, then the universe is not only larger than it appears, it is deeper in direction. The space we move through, may be the open part of a more intricate architecture. The dimensions we know may be only the broad surface of a compact, hidden world, and the laws of matter may carry, in their values and patterns, the quiet signature of geometry we have never directly seen. That is the strange promise of extra dimensions, not escape from reality, but a deeper geometry beneath it. String theory changed physics even before nature confirmed whether it is true. That may sound strange. In science, we usually imagine that a theory earns its place by making predictions, meeting experiments, and surviving direct tests. And that is still the standard. A theory that claims to describe reality must answer to reality. Mathematical beauty is not enough. Elegance is not evidence. A framework can be breathtaking and still not be the final law of the universe. But sometimes, a theory changes science in another way. It changes the questions, it changes the tools. It reveals hidden connections between ideas that once seemed unrelated. It opens doors into regions of thought that would not have been visible without it. String theory did that. Even without direct experimental confirmation as the final theory of nature, string theory has deeply influenced the way physicists think about quantum gravity, black holes, spacetime, gauge theories, and mathematics. Its impact is not only in what it claimed the universe might be, its impact is in what it taught physicists to ask. The first great fruit of string theory was its approach to quantum gravity. Gravity has always been different from the other forces. In general relativity, gravity is not simply a force acting inside spacetime. It is the curvature of spacetime itself. Quantum mechanics, meanwhile, describes the microscopic world through states, fields, probabilities, and interactions. Bringing these two frameworks together has been one of the hardest problems in physics. String theory offered a possible path. By replacing point-like particles with tiny extended strings, it softened some of the mathematical difficulties that appeared when gravity was treated quantum mechanically. More importantly, it seemed to include gravity naturally. A particular vibrational mode of the string had the properties expected of a graviton, the hypothetical quantum particle associated with gravity. This made string theory one of the first frameworks where gravity was not forced in from the outside, but appeared as part of the internal structure. That was a major conceptual shift. It suggested that gravity might not be separate from the quantum world. It might be one expression of a deeper quantum framework. Whether string theory is ultimately correct or not, that idea changed the landscape. It showed that quantum gravity could be approached with new mathematical structures, not simply by trying to copy the methods used for the other forces. It made physicists think more deeply about what it means to quantize gravity, what spacetime is, and whether the geometry of the universe might emerge from something more fundamental. Black holes became one of the most important places where these ideas bore fruit. For a long time, black holes were understood mainly through general relativity. They were regions of extreme curvature, defined by horizons and singularities. But quantum mechanics forced new questions. If a black hole radiates, what happens to the information carried by the matter that formed it? Does information disappear? Is it hidden? Is it scrambled? Is it somehow returned to the outside universe? This became one of the deepest puzzles in theoretical physics. String theory did not simply solve every black hole mystery, but it gave physicists new tools to attack them. In some special cases, string theory allowed researchers to count the microscopic states associated with certain black holes and connect those states to black hole entropy. Entropy, in broad terms, measures hidden microscopic possibilities. For black holes, this was startling. because it suggested that a black hole's thermodynamic behavior might come from underlying quantum degrees of freedom. A black hole was no longer only a geometric object. It was also a quantum system with hidden information. That changed the tone of black hole physics. Horizons became more than boundaries in spacetime. They became clues to the relationship between gravity, entropy, and information. The question was no longer just how matter falls into a black hole. It became how information is stored, scrambled, and perhaps preserved by the deepest rules of quantum gravity. This led to one of the most influential ideas connected to string theory, the holographic principle. The holographic principle, stated broadly, suggests that the information contained in a region of space may be describable by information associated with its boundary. The name comes from holograms, where a lower dimensional surface can encode the appearance of a higher dimensional image. In physics, the idea is far more precise and subtle, but the basic intuition is profound. Perhaps the contents of a volume of space-time can be represented by degrees of freedom living on a lower dimensional boundary. This was not just a poetic metaphor, it became a serious mathematical insight. String theory provided one of the clearest and most powerful examples of holography through a duality connecting a gravitational theory in one kind of space-time with a quantum field theory without gravity on its boundary. The technical details are advanced, but the conceptual impact is accessible. Gravity in a higher dimensional space may be equivalent, in certain cases, to a lower dimensional quantum theory. That idea changed everything. It suggested that space-time and gravity might not be fundamental in the way we once thought. They might emerge from quantum information. They might be different descriptions of a deeper system. The relationship between gravity and quantum theory was no longer only a conflict, it became a duality, a surprising equivalence between two languages. One language speaks of curved space-time and black holes. The other speaks of quantum fields and information. Both may describe the same underlying reality from different perspectives. This is one of string theory's greatest intellectual fruits. It gave physics a new way to think about emergence. Before this, space-time was often treated as the stage on which physics happens. Matter moves through space. Fields exist in space. Gravity curves space. But holography raised a radical possibility. The stage itself may arise from deeper quantum relationships. Geometry may be built from entanglement. Distance may be connected to patterns of information. Black holes may be revealing that the structure of space-time is tied to how quantum information is organized. These ideas are still being explored. They are not settled in a final form. But they have become central to modern theoretical physics. String theory also reshaped the study of gauge theories. Gauge theories describe the forces of the standard model, such as electromagnetism and the strong and weak nuclear interactions. They are essential to particle physics. Through string theory and its web of dualities, physicists found surprising connections between gravitational theories and gauge theories, between strongly interacting systems and more tractable descriptions, between theories that looked completely different but turned out to encode the same physics. This changed the meaning of a theory. A physical theory was no longer always one isolated description. It could have dual forms. Two theories that looked different on the surface could be mathematically equivalent underneath. One might be easier to use when interactions are weak. Another might be better when interactions are strong. What looked like separate worlds of physics could be connected by hidden bridges. Duality became one of the most powerful ideas to emerge from string theory. It taught physicists that the same reality may have more than one language. That matters because many hard problems in physics involve strong interactions, where ordinary calculation becomes difficult. If a difficult theory can be translated into an easier dual description, new questions become accessible. Even when the models are not direct descriptions of our universe, they can teach general lessons about quantum fields, gravity, thermodynamics, and information. This is why string theory influenced physics beyond its original ambition. It became a toolkit, a source of mathematical structures, a generator of analogies and exact results, a framework where quantum field theory, gravity, geometry, and information could speak to one another. Mathematics also changed under its influence. String theory opened new connections between geometry, topology, algebra, and quantum theory. It inspired developments in areas of mathematics that, at first glance, seemed far removed from physical experiment. Some mathematical discoveries were motivated by string theoretic ideas and later became important in their own right. This does not prove string theory describes nature, but it shows the depth of the structure it uncovered. A theory can be unconfirmed as physics and still fertile as mathematics. That fertility is part of its legacy. Still, the most important change may be philosophical, in the disciplined scientific sense. String theory made physicists more comfortable with the idea that the obvious ingredients of reality may not be fundamental. Particles may be vibrational states. Forces may emerge from deeper symmetries. Extra dimensions may shape observed physics. Spacetime itself may not be the final background. Gravity may be related to information in ways that were once unimaginable. It pushed the question from, what are the fundamental objects, to, what is the deeper structure from which objects, forces, and spacetime arise? That is a different kind of physics, more abstract, more mathematical, more difficult to test, but also more ambitious. The fruits of string theory are therefore mixed, but significant. It has not delivered a confirmed theory of everything. It has not produced a simple experimental signature that proves fundamental strings exist. It has not ended the search for quantum gravity. It has not resolved every black hole paradox or explained every feature of the standard model. But it has changed the intellectual landscape. It changed how physicists think about black hole entropy. It strengthened the idea that information is central to gravity. It made holography one of the most important concepts in theoretical physics. It revealed deep dualities between theories that once seemed unrelated. It enriched mathematics. It opened new ways to study quantum field theories. It raised the possibility that spacetime and geometry emerge from something deeper. In that sense, string theory's importance cannot be measured only by whether it has already become confirmed final truth. Its influence lies in the tools and questions it created. Some theories act like maps, others act like engines. String theory has often acted like an engine, generating ideas that travel far beyond the original proposal. This does not exempt it from the need for evidence. No theory should be protected from nature. If string theory is to be accepted as a description of our universe, it must eventually connect to observation in a convincing way. Scientific influence is not the same as experimental confirmation. A framework can be productive and still incomplete. It can be beautiful and still uncertain. It can be useful and still not final. That humility is necessary. But so is the recognition that science advances not only through answers, but through better questions. String theory asked whether gravity and quantum mechanics could belong to one framework. It asked whether particles could be expressions of deeper objects. It asked whether hidden dimensions could shape visible physics. It asked whether black holes are thermodynamic systems with microscopic states. It asked whether the information in a region of space might be encoded on a boundary. It asked whether space-time itself might emerge from quantum relationships. These questions now reach far beyond string theory alone. They shape research in quantum gravity, cosmology, black hole physics, and quantum information. They influence people who support string theory, people who criticize it, and people who work in neighboring approaches. That is a sign of intellectual impact. A theory has changed the field when even its unresolved problems become part of the language of modern physics. The deepest fruit may be the realization that gravity, geometry, and information are not separate topics. They may be connected at the foundation. A black hole is no longer only a cosmic sink. It is a test of information. Space-time is no longer only a stage. It may be an emergent structure. Quantum fields are no longer only theories of particles. They may be dual to worlds with gravity. These are not small shifts. They have changed how physicists imagine the hidden architecture of reality. String theory changed physics not only by offering answers, but by creating new ways to ask questions. And sometimes, at the frontier of science, a new question is almost as powerful as an answer. The deepest problem with string theory is not that it is too ambitious. Physics needs ambition. Every major step in science has required someone to imagine that nature might be simpler, stranger, or more unified than it first appears. The unification of electricity and magnetism was ambitious. General relativity was ambitious. Quantum mechanics was ambitious. The idea that stars are powered by nuclear fusion was ambitious. The idea that the universe itself had a hot, dense beginning was ambitious. Ambition is not the weakness. The weakness begins when ambition becomes difficult to test, and this is the central tension around string theory. String theory has offered one of the most mathematically developed attempts to unify quantum mechanics and gravity. It has reshaped black hole physics, inspired holography, opened new connections between fields and geometry, and influenced modern theoretical physics in ways that are difficult to overstate. It has generated deep questions and powerful tools, but it has not yet produced a clear, unique, experimentally verified prediction that confirms it as the final theory of nature. That is the problem of evidence, not the problem of imagination, not the problem of elegance, the problem of contact with the universe. Science is not only the art of building beautiful explanations, it is the discipline of letting reality answer back. A theory must eventually face observation. It must risk being wrong. It must say something about nature that can, in principle, be tested against what the universe actually does. Without that contact, even the most elegant framework remains suspended between possibility and truth. String theory has spent decades in that difficult suspension. Its core ideas are powerful. Instead of point-like particles, it imagines tiny vibrating strings. Instead of treating gravity as an outsider, it suggests gravity may arise naturally from the same framework as other particles and forces. Instead of limiting reality to the familiar dimensions of space and time, it often requires hidden extra dimensions, compactified into shapes too small to observe directly. Instead of treating space-time as simply given, it has led physicists toward the possibility that space-time itself may emerge from deeper quantum structures. These are extraordinary ideas, but extraordinary ideas require evidence, and the evidence has been hard to obtain. One major obstacle is scale. If fundamental strings exist, they may be so small that detecting them directly would require energies far beyond anything current particle accelerators can reach. The strings would not appear as tiny threads under a microscope. They would not leave simple tracks in a detector. Their characteristic effects may live at distances and energies where our experiments cannot yet go. This creates a serious challenge. If the most direct signs of string theory lie far beyond experimental reach, then how do we know whether the theory describes our universe? Physics has faced inaccessible scales before. We cannot enter the center of the sun, but we can test solar models through light, neutrinos, and helioseismology. We cannot travel to distant galaxies, but we can observe their radiation, motions, and gravitational effects. We cannot see the early universe directly at its earliest moments, but we can study the cosmic microwave background and the distribution of matter. Indirect evidence can be powerful, but it must be specific. It must narrow possibilities. It must give nature a way to disagree. This is where string theory struggles. The framework is extremely rich, but that richness can make it difficult to extract one clear experimental prediction. If a theory allows many possible versions of low-energy physics, then discovering that our universe has one particular set of particles and forces may not uniquely confirm the theory. The same broad framework might allow many different universes with different properties. This is the landscape problem. String theory does not appear to give one single obvious solution that leads uniquely to the universe we observe. The extra dimensions can be compactified in many possible ways. Different shapes can lead to different particles, forces, constants, and physical laws at accessible energies. The result is a vast space of possible solutions, often called the landscape. For some physicists, this is a profound clue. Maybe the universe we observe is one region in a much larger range of possible physical realities. Maybe cosmology selects one solution. Maybe some version of the multiverse is involved. Maybe what we call fundamental constants are environmental features, not unique necessities. For other physicists, this is a warning sign. If a theory can accommodate too many possible outcomes, it becomes harder to test. A theory that explains almost anything after the fact may struggle to predict something before the fact. The danger is not that string theory says nothing. The danger is that it may say too much. Scientific power depends on constraint. A strong theory does not merely fit known facts. It limits what can happen. It makes the universe less arbitrary. It gives us reasons why nature must behave one way rather than another. If string theory is to become the final theory of nature, it must eventually do more than provide a possible home for our universe. It must show why our universe belongs to the theory in a testable way. That is difficult. And it is one reason string theory remains controversial. There are possible signatures people have looked for. Extra dimensions might, in some scenarios, produce effects at high-energy colliders or in short-distance gravity experiments. Supersymmetry, a mathematical symmetry often connected with string theory, might reveal partner particles beyond the standard model. Cosmic strings, remnants from the early universe in some models, might leave gravitational or cosmological signals. Certain patterns in cosmology, black holes, or particle physics might point toward deeper string-like structure. But so far, no decisive signal has confirmed the theory. No unmistakable extra dimension. No confirmed supersymmetric particles. No direct observation of fundamental strings. No unique experimental fingerprint that says, this is string theory and not something else. This absence does not prove string theory is wrong. That is important. A theory can be difficult to test before technology or observation reaches the relevant domain. The lack of current evidence is not the same as disproof. String theory may still describe nature at scales we cannot yet access. It may produce indirect predictions through future advances in cosmology, gravitational waves, black hole physics, or particle experiments. It may need a deeper formulation before its connection to observation becomes clear. But the absence of confirmation does mean we must be honest. String theory is not established as the final theory of the universe. It is a candidate, a powerful one, a productive one, a controversial one, but still a candidate. This distinction matters because the public often hears about string theory in extremes. One extreme presents it as the theory of everything, as if physics has already discovered the final code beneath reality. The other dismisses it as pure fantasy, detached from science because it has not yet been directly tested. Both views are too simple. String theory is not confirmed truth, but it is not empty imagination. It is a serious mathematical framework developed to address real problems in physics: quantum gravity, black holes, unification, the nature of spacetime. It has produced insights that influenced areas far beyond its original scope. It has revealed surprising connections between gravity, quantum field theory, geometry, and information. Yet seriousness does not replace evidence. This is the balance science requires. A theory can be deep and unconfirmed, beautiful and uncertain, useful and not final, mathematically rich and experimentally unresolved. String theory lives in that tension. The problem of evidence also raises a deeper question about the frontier of physics. What happens when the theories we need to describe the deepest scales of reality require energies we cannot reach? What happens when the universe hides its fundamental structure behind a wall of scale, distance, and experimental limitation? How long can a theory remain fruitful without decisive tests? What counts as evidence when direct observation may be impossible for generations? These questions are not only about string theory, they are about the future of fundamental physics. The 20th century gave physicists extraordinary experimental access. Particle accelerators discovered new particles. Telescopes revealed cosmic expansion and the early universe. Precision measurements tested quantum mechanics and relativity. Theory and experiment moved together in dramatic ways, but the deepest remaining questions may be harder. Quantum gravity may live near scales far beyond direct experiment. The earliest moments of the universe may be hidden behind cosmic limits. The interiors of black holes may be inaccessible by definition. Dark matter and dark energy may interact with ordinary matter only weakly or in ways we do not yet understand. At the frontier, nature may not hand over evidence easily. This does not mean we abandon the demand for evidence. It means we must be more creative, more careful, and more honest about what we know and what we do not. We look for indirect signatures. We develop mathematical consistency tests. We compare theories against known physics. We search for cosmological imprints, gravitational wave signals, particle deviations, and black hole clues. We refine competing approaches. Science continues, but it cannot pretend uncertainty has been resolved before it has. String theory's greatest weakness is not ambition. It is the difficulty of testing whether the ambition describes our universe. That weakness is serious. It is not a minor detail to be brushed aside. A theory that aims to explain everything must eventually explain this world, not just possible worlds. It must connect its deep structure to measurable reality. It must show why the particles, forces, constants, and space-time we observe arise from its principles. It must move from mathematical possibility toward physical necessity. Until then, string theory remains unfinished. But unfinished does not mean worthless. Some of the most important ideas in science spend long periods in uncertain form. They develop, split, merge, inspire tools, and sometimes lead to unexpected discoveries. Even if string theory is not the final answer, it may be a bridge toward one. It may have taught physics lessons that survive even if the original framework changes. Holography, duality, black hole microstates, and the deep connection between gravity and information may continue to shape science regardless of string theory's final status. That is why dismissing it too quickly would be careless, but accepting it too quickly would also be careless. The proper attitude is disciplined openness. String theory deserves attention because it addresses real problems and has produced profound insights. It deserves criticism because evidence remains incomplete. It deserves neither blind faith nor easy rejection. It deserves the same standard every theory ultimately faces. Does nature agree? That question remains unanswered. And in that unanswered space, string theory becomes a lesson in scientific humility. The universe is not obligated to reward our most beautiful ideas. It is not required to be mathematically elegant in the way we prefer. It may be simpler than string theory. It may be stranger. It may be described by a version of string theory, not yet fully understood. Or it may require a completely different framework waiting beyond current imagination. We do not know. But knowing that we do not know is part of science. The dream of string theory is powerful. One deep structure behind particles, forces, gravity, and spacetime. The challenge is equally powerful, to find out whether that dream belongs to the real universe. Until evidence becomes clear, string theory remains one of the most beautiful and uncertain ideas in modern physics, a theory still waiting for nature to answer. String theory still matters because the questions that created it have not disappeared. Gravity is still not fully quantum. Black holes still press against the edge of our understanding. The beginning of the universe still points toward conditions where space-time and quantum mechanics must somehow belong to one deeper description. The standard model still does not include gravity. Dark matter remains unidentified. Dark energy remains mysterious. And the deepest structure of space-time is still not known. So physicists continue to study string theory not because it has already won, and not because it has been confirmed as the final theory of nature. They study it because it remains one of the most developed frameworks ever built for asking what quantum gravity might be. It offers mathematical tools, conceptual structures, and unexpected bridges between areas of physics that once seemed separate. Even if string theory is not the final answer, it has expanded the map of what physics can be. That is a different kind of importance. A confirmed theory explains nature directly. A useful framework may do something else. It may reveal hidden relationships, open new paths, and give scientists language for questions they could not previously formulate. String theory has done that again and again. It has shown that gravity, geometry, quantum fields, thermodynamics, and information may be more deeply connected than 20th century physics first suggested. One reason string theory remains important is that quantum gravity remains unfinished. General relativity describes gravity as the curvature of spacetime. Quantum mechanics describes matter and radiation through states, fields, uncertainty, and probability. Both theories are extraordinarily successful in their own domains. But in places where gravity is strong and quantum effects matter, neither theory alone is enough. String theory offers one possible way to merge them. It does this by changing the basic picture. Instead of treating the fundamental ingredients as point-like particles, it imagines tiny extended strings whose vibrational states appear as particles. In many versions of the theory, a vibrational mode appears with the properties expected of a graviton, the hypothetical quantum carrier of gravity. That means gravity is not added awkwardly from outside. It emerges within the framework itself. That feature remains one of the reasons the theory is taken seriously. A theory of quantum gravity should not merely place quantum particles inside a fixed space-time background. It should help explain how space-time and gravity fit into quantum reality. String theory has provided many of the most detailed attempts to do this. It is not the only approach, and it is not experimentally confirmed, but it has developed a vast mathematical structure around the problem. That structure has become part of modern theoretical physics. Black holes are one of the places where string theory's influence is especially strong. Black holes are not just extreme astronomical objects. They are testing grounds for the deepest laws. They combine gravity, thermodynamics, quantum mechanics, and information in one system. They force physicists to ask what happens to information when matter falls behind a horizon. They force questions about entropy, radiation, microscopic states, and the limits of space-time. String theory helped sharpen these questions. In certain carefully defined cases, it gave physicists a way to count microscopic states associated with black holes and relate them to black hole entropy. This mattered because it suggested that black holes are not merely smooth geometric objects in general relativity. They may have an underlying quantum structure, a hidden accounting of states that gives rise to their thermodynamic behavior. That idea changed the emotional and scientific meaning of black holes. A black hole is no longer only a place where gravity becomes extreme. It is a clue about how information and space-time are connected. This connection became even more powerful through holography. The holographic principle suggests, in broad terms, that information in a region of space may be described by information on a boundary. String theory provided some of the strongest mathematical examples of this idea, showing that a gravitational world in one description can be equivalent to a quantum field theory without gravity in another. The details are advanced, but the meaning is profound. Gravity and quantum fields may be two languages for the same underlying physics. Space-time may not be fundamental in the way it appears. A region with gravity may be encoded by a lower-dimensional quantum system. This changed how physicists think about the universe. It suggested that geometry might emerge from information. Distance might be connected to entanglement. The smoothness of space-time might arise from deeper quantum relationships. These ideas now extend far beyond string theory itself. They influence research in black hole physics, quantum information, condensed matter theory, cosmology, and the foundations of quantum gravity. This is one reason string theory remains alive. Some of its most important offspring no longer depend entirely on whether the original picture of tiny vibrating strings turns out to be the literal final description of nature. The tools and insights have entered the wider bloodstream of physics. Duality is another major reason string theory still matters. A duality is a deep equivalence between two theories that look different on the surface. One description may involve gravity, another may involve quantum fields. One may be hard to calculate when interactions are strong, another may become easier in that same regime. Two languages, one underlying reality. This is a powerful idea because physics often becomes difficult when systems are strongly interacting. Ordinary methods may fail, but if a hard problem can be translated into a dual description where it becomes simpler, new understanding becomes possible. String theory revealed many such dualities. These dualities change the way theorists think about physical laws. A theory may not have only one face. The same physics may appear in different mathematical forms, each useful in different conditions. What looks like a particle in one description may look like geometry in another. What looks like gravity in one framework may be encoded in a quantum system in another. This is more than a technical trick. It suggests that our usual categories may not be fundamental. Particles, fields, strings, branes, geometry, and information may be different windows into a deeper structure. If so, the language we use to describe reality may depend on the scale, energy, and perspective from which we ask the question. String theory has also influenced cosmology, even where the connection remains speculative. The early universe was an extreme environment where high energy, quantum fields, and gravity all mattered. String theory offers possible ways to think about what happened near the beginning of cosmic history, how extra dimensions might have shaped physical laws, how inflation might connect to deeper fields, and how different vacuum states might relate to the values of constants in our universe. These ideas are not settled. Many remain difficult to test, but they show how string theory expanded the imagination of cosmology. It made physicists consider that the structure of the universe might depend on hidden dimensions, compact geometry, branes, and vacuum choices. It suggested that the laws we observe might be connected to a deeper landscape of possibilities. That idea is controversial, but it has forced serious discussion about what explanation means when a theory permits many possible universes. Even criticism of string theory has changed physics. The demand for evidence has become sharper. The question of testability has become more urgent. The relationship between mathematical elegance and empirical science has become a central philosophical and scientific issue. String theory's difficulties have pushed physicists to think more carefully about how theories at inaccessible scales can be judged, compared, constrained, or connected to observation. That is part of its influence too. A powerful theory does not only inspire supporters, it also forces its critics to refine their arguments. String theory matters in theoretical mathematics as well. Its structures have generated unexpected connections in geometry, topology, algebra, and other fields. Ideas motivated by string theory have helped mathematicians discover relationships that might not have appeared otherwise. Sometimes physics acts like a compass for mathematics, pointing toward patterns before they are fully proven in formal terms. String theory has done this repeatedly. Again, mathematical fertility does not prove physical truth, but it shows that the theory is not empty. It contains structure, and deep structure often leaves traces across disciplines. The relationship between string theory and quantum information is especially important today. Quantum information began partly as a field concerned with computation, communication, entanglement, and measurement. But it has become increasingly central to questions about gravity and space-time. Black hole information, holography, entanglement entropy, and the emergence of geometry now sit at the intersection of quantum information and quantum gravity. String theory helped build some of the bridges to that intersection. It encouraged the idea that space-time may be encoded, that geometry may arise from entanglement, and that black holes are not simply gravitational objects but information-theoretic systems. These ideas are still developing, but they are among the most active and exciting areas of theoretical physics. In this way, string theory's legacy has become broader than its original promise. The original dream was a theory of everything: particles, forces, gravity, and space-time unified in one framework. That dream remains unconfirmed, but along the way, string theory created tools that changed how physicists approach some of the hardest problems in science. It gave new language to quantum gravity. It deepened black hole thermodynamics. It made holography central. It revealed dualities between theories. It connected gauge theories and gravity. It influenced mathematics. It pushed cosmology into new conceptual territory. It helped place information near the center of fundamental physics. This is why many physicists still study it, not because every question is solved, because many of the best questions now pass through the territory string theory opened. There is also a practical reason. A fully consistent quantum theory that includes gravity is extremely difficult to build. String theory remains one of the few frameworks with enough internal structure to explore such questions in detail. It may be incomplete. It may not describe our universe exactly. It may eventually be replaced. But it is still a rich laboratory for ideas about quantum gravity. At the frontier, a theoretical framework can be valuable even before final confirmation if it lets scientists calculate, compare, and discover connections that would otherwise remain hidden. String theory has provided such a laboratory for decades. The danger is mistaking that value for proof. The equal danger is mistaking lack of proof for lack of value. The honest position is more careful. String theory is not experimentally established as the final theory of nature. It has serious challenges, especially the problem of testability and the vast landscape of possible solutions. But it has also produced some of the deepest insights in modern theoretical physics. It has helped reshape the search for quantum gravity and change the way physicists think about black holes, information, and space-time. It remains important because the problems it confronts remain important. The universe still asks how quantum mechanics and gravity fit together. Black holes still challenge our understanding of information. The early universe still hides the place where space-time and quantum fields met under extreme conditions. The standard model still leaves gravity outside. And space-time itself may still be waiting for a deeper explanation. String theory may or may not be the final answer, but it has expanded the map of possible answers. It showed that particles might be vibrations. It showed that hidden dimensions might shape visible physics. It showed that gravity might be encoded in a quantum theory without gravity. It showed that black holes might be understood through microscopic states. It showed that information may be woven into the fabric of space-time more deeply than anyone expected. That is not a small legacy. At the deepest level, string theory still matters because science is not only a collection of confirmed facts. It is also the disciplined exploration of possible structures, guided by mathematics, constrained by known physics, and always waiting for nature to answer. Some paths lead directly to confirmation. Some lead to correction. Some lead to tools that outlive the original theory. Some become bridges. String theory may be a final road, or it may be a bridge, but either way, it has changed the landscape it crosses. Even if string theory is not the final answer, it has expanded the map of what physics can be. String theory remains one of the most beautiful unfinished stories in modern physics. It began with a longing for unity. Not a simple kind of unity, not a neat slogan, but a serious scientific hope that the deepest divisions in physics might be shadows of a single structure we had not yet fully understood. Quantum mechanics describes the microscopic world with astonishing precision. General relativity describes gravity, space-time, black holes, and the expanding universe with equal power. The standard model organizes known particles and forces, but leaves gravity outside its framework. Cosmology points toward dark matter, dark energy, and the earliest moments of the universe, where our theories approach their limits. String theory tried to reach beneath all of this. It asked whether particles might not be the final ingredients of nature. It asked whether what we call electrons, quarks, photons, and perhaps even gravitons could be different expressions of something deeper. It imagined that tiny vibrating strings, not point-like particles, might form the hidden basis of matter and force. It suggested that gravity could arise naturally within a quantum framework. It opened the possibility that extra dimensions, curled up beyond ordinary perception, might help shape the particles and forces we observe. It was an extraordinary idea, and it still is. But the universe has not yet confirmed whether it is true. That is the central tension. String theory tried to explain everything, but nature has not yet answered clearly. It has not given us a direct sighting of a fundamental string. It has not given us a unique experimental prediction that forces the theory into reality. It has not shown us extra dimensions in a way that cannot be explained otherwise. It has not revealed supersymmetric particles in a form that confirms the framework. It has not yet become the final language of nature. A beautiful theory must still answer to nature. This is not a failure of imagination. It is the discipline of science. Physics is not only a search for elegance, it is a negotiation with reality. Theories can be graceful, powerful, and mathematically rich, but the universe is the final judge. Nature does not have to follow the path that seems most unified to the human mind. It does not have to reward beauty. It does not have to make its deepest laws accessible to our current machines. That humility is essential. String theory deserves neither blind belief nor easy dismissal. It is not established fact, but it is not empty fantasy either. It grew from real problems: the need to reconcile quantum mechanics with gravity, the mysteries of black holes, the breakdown of known theories at extreme scales, and the search for a deeper structure beneath the standard model. It developed into one of the richest mathematical frameworks physics has ever produced. It changed how scientists think about space-time, information, geometry, and the possible unity of forces. Even if string theory is not the final answer, it has already changed the questions. It made black holes look less like endings and more like clues. A black hole is no longer only a region where gravity becomes extreme. It is also a system that forces us to ask what information is, where it goes, and whether space-time itself preserves it in some hidden form. String theory helped give physicists tools to think about black hole entropy, microscopic states, and the deep relationship between gravity and quantum mechanics. It helped make the holographic principle central to modern physics. The idea that information in a volume of space might be encoded on a boundary sounds almost impossible at first, but it has become one of the most profound ideas to emerge from the search for quantum gravity. It suggests that space-time may not be as fundamental as it appears. Geometry may arise from quantum relationships. Gravity may have an information-theoretic face. A region of space may be understood through a very different description living at its edge. These ideas now reach beyond string theory itself. They influence quantum information, black hole physics, cosmology, and the study of space-time emergence. They have made physicists wonder whether the fabric of reality is not woven from space alone, but from entanglement, information, and hidden mathematical structure. They have turned the search for quantum gravity into something deeper than just adding one more force to a list. They have made the question of space-time itself feel open. That may be one of string theory's greatest legacies. It taught physics to doubt the obviousness of the stage. For centuries, space and time felt like the background of existence. Things happen in space. Events unfold in time. Matter moves. Light travels. Gravity bends paths. But modern physics has slowly made the stage more active. Relativity showed that spacetime can curve, stretch, and respond to matter. Quantum theory suggested that fields and particles do not behave like ordinary objects. String theory pushed the question further. Perhaps spacetime itself is not the final foundation. Perhaps it emerges. Perhaps it has hidden dimensions. Perhaps geometry is one language for something deeper. Perhaps what looks like space at large scales is the smooth surface of a more fundamental quantum structure. These are not settled conclusions. They are not confirmed facts. But they are serious ideas that change the frontier. This is why string theory remains both powerful and unresolved. It gave physics a vision of unity, but not yet a decisive proof. It produced mathematical richness, but not yet a clear experimental signature. It suggested that the universe may be built from a deeper language, but has not yet shown that this language is the one nature actually speaks. There is a quiet lesson in that uncertainty. Science is not a straight path from beautiful idea to final truth. Sometimes it moves through partial maps, unfinished structures, and theories that illuminate more than they confirm. Some ideas are stepping stones, some are scaffolding, some become final pillars, some are replaced but leave behind tools that remain. The history of physics is full of such transitions. Old theories can be wrong in one sense and still essential in another. They can fail as final descriptions and succeed as bridges. String theory may be a bridge, or it may be a path. We do not yet know. If it is a path, then perhaps one day it will connect directly to observation. Perhaps future experiments, cosmological data, gravitational wave signals, black hole studies, or new mathematical breakthroughs will reveal a clear sign. Perhaps the hidden dimensions will leave an imprint. Perhaps the theory will produce a prediction so precise and unexpected that nature can answer. Perhaps the long silence will break. If it is a bridge, then its role may be different but still profound. It may guide physics toward a deeper framework that is not exactly string theory as we know it. It may teach us that holography, duality, quantum information, and emergent space-time are the true lasting clues. It may be remembered not as the final theory, but as the structure that allowed physics to imagine the next one. Either way, it changed the dream. Before string theory, the search for unity had a different shape. Gravity and quantum mechanics seemed divided by language, scale, and method. Particles were treated as fundamental points. Space-time was often treated as the arena. Black holes were extreme solutions of relativity. Information belonged mostly to quantum theory and thermodynamics. After string theory, the boundaries shifted. Particles might be vibrations. Geometry might determine physics. Gravity might be holographic. Black holes might store information in ways that reveal the microscopic structure of space-time. Different theories might be dual descriptions of the same reality. The universe might be less like a collection of separate ingredients and more like a set of interlocking languages. That is a major change in thought. It is also a reminder that the deepest theories are not only about calculation, they are about perspective. A powerful theory changes what scientists consider possible. It expands the imagination while still demanding discipline. It opens doors, but the universe decides which doors lead somewhere real. String theory remains beautiful because it offers a vision of coherence. It suggests that the scattered pieces of modern physics might not be scattered at all, that matter, force, gravity, and space-time might be different faces of one hidden order, that the complexity of the cosmos might arise from a simpler underlying structure, not simple in appearance, but unified in principle. And yet, its beauty must remain humble. The universe is older than our mathematics. It is deeper than our metaphors. It is not required to make itself elegant for us. A theory can feel inevitable inside the mind and still be incomplete in nature. The final test is not whether we can admire it. The final test is whether the world behaves as it says. For now, string theory waits. Not abandoned, not confirmed. Waiting in the difficult space where the deepest ideas often live. It has roots in one of the greatest problems in science: how to reconcile the smallest rules of matter with the largest rules of spacetime. It has fruits that still nourish physics: holography, duality, black hole insights, mathematical structures, and new ways of thinking about information and geometry. But between roots and fruits, the central question remains open. Is this the language of reality, or only a language that points toward one still beyond us? There is no shame in that uncertainty. It is the honest condition of the frontier. The edge of knowledge is not where science ends. It is where science becomes most careful. It is where ambition has to meet patience. It is where beauty must wait for evidence. String theory may be a path to the deepest rules of the universe, or it may be a bridge toward a theory still beyond us. Either way, it changed how physics dreams of unity. Good night, and see you in the next video.